use a laptop, computer on overnight business trips. State the hypothesis that can be used to test the assumption. This is good practice for the diagnosis part. Hypothesis testing, how to set up the problem process. The assumption is that 2/3 of business travelers use a laptop. What is the null hypothesis?
Not use. Do not use.
You see, we need a bit more.
1/3 of business travelers do not use a laptop on overnight travel.
Let's try to do it in terms of a proportion. P.
P equals 2/3.
P equals 2/3. Yes. Why?
Because the airline said it did. And we're in agreement.
Okay. Because the airline said it did. That's good. It's not quite why we put it in the null.
It's easier to test for 2/3 than it is to test for every other.
Exactly. In fact, testing for everything else is impossible. So, since this is in fact possible, it's the only way we can proceed. What is the alternative?
Not
P
equal.
is not equal to 2/3.
Now, we're told to sample 546 travelers. Is that a large enough sample size?
Yeah. Yes.
Because?
Because both the third and the 2/3 are greater than 5.
Exactly. So, just look at the smaller of the two proportions. 2/3 and 1/3. The smaller of those is 1/3, right? 1/3 of 546 is more than 5. So, we're good to go. Any questions on checking that? All right. In that case, we, let's see, we have the first step, and we also have that 355 business travelers out of the 546 were in fact laptop users. Under the null hypothesis, what is the mean of the distribution of p-bar?
Is it?
A little louder.
0.75.
Can't hear you.
Is it 0.75?
Why?
It's 2/3.
Oh, 2/3 is 676.
Yeah.
But yes, it's 2/3.
It's not
And I forget if I've told you all this, but if I have, then I'm sorry for repeating myself. When you speak very softly, and this is not a big problem, but if you speak softly and there is some other sound around, I can't hear anything. I was 25 years old before I realized that people could listen to music and hear lyrics. They just don't really exist for me. So when there are multiple people having a conversation, for instance, it's all just gone, which of course makes going to a nightclub really odd. But anyway, so when I say, I can't hear you, I'm not saying it just because I'm being difficult. It's I can't hear you. But it's very strange. It took me a long time to figure out what was going on too, because at home, when there's no other sound, I can have the TV on quite low, no problem. But if there's any amount of sound around, then it won't work. So we have the null. What's the and the alternative? That's step 1. What's step 2? Reject region. And in order to find a reject region, what do we need? use an output of 5%.
What is the symbol you used for that, 355?
Oh, that's just an F. So I did that so that we can calculate P bar as F over N. So 355 over 546. Remember way back in probability we used F over N? Doesn't. That's all right. That's right, I'm making it up as I go along. So that is 0.6502. But that's sort of skipping ahead a little bit. Okay, where shall we put our rejection region?
Both sides.
Both sides, very good. And so we know yet again that the critical values are going to be minus 1.96 and 1.96, and therefore the rejection region is
Anything was right and left of 1.96. Minus 1.96 and
okay, there we go. Very good. 2.
Yep.
Any questions on that? Okay. What's step 3?
Standard statistics.
Mary?
Standardized test statistics.
Excellent. So that's P bar minus P naught divided by the standard deviation of P bar, which in this case is P naught, minus P naught over N. So we have not 2/3. So we got 355 over 546 minus 2/3 over 2/3 or minus 2/3 divided by 546. And I'm always tempted to do this incorrectly, but this is, I believe, is correct. And that number is not as interesting as a minus 0.82. Is that number in our projection region? And so, step 4, our conclusion, the standardized test statistic is not in the rejection region, and therefore we
Fail to reject.
fail to reject. Good. So what do we conclude in terms of the problem?
their claim is true. We fail to reject that two-thirds of business users use laptops.
Yes, right. So you're changing your answer to the second part? Or is that one answer? Okay, the first part of your answer was that you conclude that the claim is true, that 2/3 of business travelers use laptop. You sure you want to keep that? Good. Is that the same thing as concluding that 2/3 of business travelers use laptop?
No, we can't prove it, so.
Exactly. So there is insufficient evidence to conclude that any other number than 2/3 is correct. However, we cannot conclude that exactly 2/3 of business travelers in the population use a laptop. Everybody happy with that? Sure. We failed to reject the null hypothesis, and therefore we have to say that there's insufficient evidence to conclude that the proportion of business travelers in the population that use a laptop is different from 2/3. Now, that means that the proportion could be, 0.66 in reality, right? Or 0.65 for that matter, which is different from 2/3. But there's not enough evidence for us to reject the null hypothesis. It's not the same thing as concluding that the null hypothesis is true. We're back to that original question again.
What if we had done the other way, like alternate, we switched the hypothesis?
You can't. You can't. There's no way you can construct a distribution for the test statistic if your null hypothesis is that P is different from 2/3.
Huge distribution.
Well, no, that's not really the issue. The distribution always has, remember, the area under the curve has to be 1, right? So, what? How would we center this distribution?
How do we calculate?
What's the mean of the distribution under the null if the null hypothesis is that P is different from 2/3? If I put this on the 5-minute, it might take you a while before you realize that it's a trick question. There's no way you can answer that question. I won't put up a final, but I mean, it's a trick. There's no way you can do that. Now, if we wanted to say, if the airline had claimed that more than 2/3 of business travelers use a laptop, that is something we could set up in 2 different ways, right? So let's just do that. It might be confusing. If the airline is claiming we want to show that more than 2/3 of business travelers use a laptop, what would be the appropriate null?
It's greater than.
Greater than.
Is it
Or
greater
equal to.
Well, what would be the null hypothesis?
Less
P
false.
is greater than or equal
Uh,
Less than.
like this?
Right.
Well,
No,
Evan?
yeah, because what did you, less than equal to?
Well, okay, so we have 2 candidates. And clearly, it would be possible for you to do the test both ways, right? There's no problem with that. In fact, in both cases, you would use the same mean of 2/3 under the distribution for PUR. But in this case, the 2 conclusions you can get are, there's insufficient evidence to conclude that less than 2/3 of, there's insufficient evidence to reject the null hypothesis that at least 2/3 use a laptop, and therefore say that less than 2/3 use a laptop. And in this case, you'd have to say that there's insufficient evidence to conclude that 2/3 or fewer use a laptop. I'm sorry, there's insufficient, confusing myself now. There's insufficient evidence to reject the null hypothesis that 2/3 or fewer use a laptop, and therefore conclude that more than 2/3 use a laptop. Or you could conclude that more than 2/3 of airline travelers use a laptop in the second case. And if that's what you want to be able to claim, that more than 2/3 of business travelers use a laptop, you have to use this structure, right? The only positive claim you could make in this case is that fewer than 2/3 of business travelers use a laptop. Yes? Maybe? No? Maybe? Maybe? Okay. Well, set it up and just ask yourself, what is the positive claim you can make? Well, the positive claim is going to be an alternative, right? If the only thing you can do with the null is fail to reject it. You never accept the null. That's the key point here. All right. Other questions on that?
Back on the original one, would a valid null be that the number of travelers that don't use a laptop is 1/3?
Yes,
Okay.
but that's testing the same thing.
Right. see how flipping it the other way doesn't get us there. I didn't know if,
Well, no, I mean, that's literally the same thing. It would
Right.
give you the exact same result, because you would have 546 minus 355 in the numerator, and that would be exactly 0.82 standard deviations away from the mean in any case, so you get the same result. Because notice, even here, you have 2/3 and then you have 1/3 here, so you have the exact same standard deviation, you have the exact same distance from the mean.
okay.
Alright, good. So that's the traditional approach. What's my next question?
P-value.
P-value. And based on what we've done, we can at least say something about p-value. Better than alpha. Very good. So minus 0.82 is something like here, right? What should I shade it? Okay. So this piece. And that piece is
2061.
no, what I'm asking is this the whole p-value?
That's half.
Very good. It's half the p-value. And you have 0.82. And that also is half the p-value. So what do you look up in order to find the p-value?
Z.
And what is z?
Z is 0.2939.
I hope not.
For 0.82.
Oh, no, you've already looked up z. What I was asking, what did you use to look up? What number? Okay, you looked this up, right? And then use that, okay, so I just wanted to make sure everybody's on the same page. You look up 0.82,
Right.
and you told me point,
0.2939.
okay? So, that gives you this piece, and then that means that that half the p-value is equal to what?
0.5.
Good. P-value is then equal to 2 times 0.2061 or 0.4122. Is that consistent with our earlier conclusion?
Yes.
Is that consistent or inconsistent? It is consistent, very good. So p-value is greater than alpha, we again fail to reject the null. Questions on that? Alright, as a, just sketch, if there are no questions, I'll remove that and we'll do a little bit of this, of the quality associates problem, because it too tends to cause some confusion. Can you erase this? Just making sure. I feel really unfortunate if I have to write it again. Okay, so quality associates, this is case problem 1. And the reason I like it is that it's a, quality control is a huge application in reality. And we get to see an additional type of chart. So case 1, it's page 384, 385, 385 and the 5th edition. So this is Quality Associates. And essentially, the process here is a machine production of something. Let's call it a widget. They take a sample of 800 observations, and based on the sample of 800 observations, they calculate a standard deviation of 0.21. Now, they then decide that the population standard deviation is 0.21 based on our sample of 800. Is it legitimate to use a sample statistic as a population parameter? You can answer either way here, so there's really, you know, as long as you have reasonable backing for your statement, either way is fine.
No,
No, because,
it's population, you can't really.
okay, it's true. You can't know sigma.
Yes, because it's a consistent process.
That's also true. It's going to be very, very close, right? 800 observations is a very, very large amount. But there's one other argument that I wouldn't, you know, that's not obvious. But if you think about this, the machine is going to produce maybe day in, day out, maybe year in, year out, right? When it goes out of whack, what you want to be able to do is calculate a standardized test statistic, right? You want to be able to observe that it has in fact gone out of whack. But when it does, you want to use the standard deviation from when it is working well. Yes? So you need some estimate for the standard deviation when the machine is fine, not a new estimate of the standard deviation every time you take a new sample. It's kind of like the idea of using P-naught when you're calculating a standardized test statistic for a proportion. You need to assume everything is fine, and then and only then do you move on and reject the null if you get a large enough or a result that's strange enough. Okay, the machine is supposed to produce with a mean of 12. That's the calibration. And so if the mean is anything other than 12, the machine is out of whack. Even if it's 11.99999999992. What's the null hypothesis? Yes. For the same reason as what we just discussed, it's the only possible null hypothesis. They're going to take a sample of 30 observations every day or hour, whatever it is. Well, we're taking periodically. So. And this is actually done. I remember I was supposed to organize a tour of the Eaton supercharger factory for a bunch of visiting statisticians, and it does use quality control, and they do test a certain number of observations each, I don't know, 2 hours or whatever. And there, I have to admit, they had some very, very impressive tolerances, because those little machine bits, do you know how fast they spin? Does everybody know what a
13,000
supercharger is?
RPM.
Supercharger is something you run on a belt from your engine that forces air into your engine at a higher pressure than the air from the atmosphere. So where a turbo runs with gas, this runs on a belt. Dave, you know this.
Yes. It's a belt-driven air compressor that
Right.
on the intake side of the engine.
And you know,
The Eaton superchargers, they generally run between 10 and 13,000 RPM at their peak efficiency. They roll off around 16,000 RPM.
they roll off?
Their efficiency rolls off. They heat soak.
Oh, okay.
The heat generated in compressing the air is so much that it's offsetting the power gains from further compression.
Okay. Yeah, I was told they maxed out at 15,000, so yeah. But I'm just amazed, 15,000 RPM, that thing is flying.
Yes.
Your tolerances obviously have to be thereafter. Now, you're given data. You look in your book, you have 4 samples of 30 observations, right? Now, obviously, on a final, I wouldn't be giving you this, but as a project, this would be perfectly feasible. Now, for each of these, however, in the interest of doing this in a reasonable amount of time, we instead report a certain amount of information. We have samples, 1, 2, 3, and 4. For each of the samples, we gather 30 observations and calculate a mean of 11.96, 12.03, 11.89, 12.08. And just for grins, we calculate standard deviations of 0.2204, 0.2204, 0.2072, and 0.2061. Do these seem out of whack with the hypothesized population standard deviation? They seem pretty close, right? Okay, we can then also calculate a standard error of the mean. Well, it actually turns out to be the same in each case, so we won't bother. But we can calculate a standardized test statistic, which is minus 1.08, 0.75, minus 2.90, and 2.12. Now, just based on what you know so far, including hinted empirical rules, which one of these might seem suspicious? Fourth one? So this one? Okay. Let's look at the distribution under the null hypothesis. So under the null hypothesis, X bar has a mean of 12, good. And we're going to use an alpha of 0.01. Oops. And it's a two-sided test. So we're only going to have 0.005 on each side. And that gives us a Z of 2.576 and minus 2.576. So the rejection region here is, sorry?
Minus infinity from negative 2.576, union 2.576, positive infinity.
Perfection. Okay, now knowing the rejection region, take another look at our standardized test statistics. Do any of these follow the rejection region?
Third one?
Third.
The third one.
Right. And what did I do with my red pen? Okay, so here. For the third observation, third sample, we reject the null hypothesis. Is it then possible to make a type 1 error? This is not a fair question.
Type 1 is you already rejected.
Exactly. We reject a true null. That's a type 1 error. Is it possible that we made a type 1 error in the third sample here?
Yes.
Yes, right, because we rejected. Likewise, we could have made a type 2 here, here, or here. But we don't know. Let's think about the consequences though. Here, we failed to reject that the machine is well calibrated. What would a type 2 error mean in practical terms? in the first sample, we failed to reject the null hypothesis that the machine is well calibrated. So what practical results would come from that?
That it wasn't calibrated. You failed to reject it when it was off.
Right, exactly. So your machine is running haywire, but you do nothing. That's the danger of a type 2 error in that case, right? In the third case, what would be happening? What would be the result?
You rejected it when it was one.
Exactly. So what, in practical terms, when you reject the null hypothesis that the machine is well calibrated, you take what action?
Try to calibrate it.
Yes, you recalibrate a machine that's fine, basically. Now, so this is one of those cases where when you talk about the types, at least I think type 2 sounds worse than type 1, right? I mean, think about this being your car. You do a type 1 error, you change the oil, for instance, when you didn't need, or better yet, timing belt. You change this timing belt when in fact you didn't need to. What happens? Well, you're out a few dollars, but at least your engine doesn't explode. You check your maintenance log or take a look at it and decide, oh, everything's fine. And in fact, 100 miles down the road, the timing belt blows, and your engine goes bye-bye. That would be then the result of a type 2 error, right? So in a quality control setting, I would argue that type 2 is actually worse. The problem is, again, we're running into that requirement that you be able to construct a distribution for the test statistic under the null. Okay, so this last part is a control chart. We're going to come up with an upper limit and a lower limit in terms of x bar, so that if x bar is above the upper limit or below the lower limit, we will stop the process and recalibrate. We have enough information here to calculate where those limits lie.
12 plus 2.576.
12 plus 2.576. Almost.
Is that upper level or lower?
Well, 12 plus would be this way, right?
Yeah. It's upper level. You,
That's supposed to be.
Right. Let's see, you. Not a very good one, perhaps, but
12 minus 2.5.
I'm sorry?
Yeah. I mean lower level.
Okay, so the lower level would be 12 minus 2.576. Actually, it's not quite right yet, so we need to. It's plus 2.576. Now, 2.576 is standard deviations, right? That's the number of standard deviations above the mean.
Okay.
So it's not just 12 plus 2.576, it's 12 plus,
Into.
2.576 times 0.21.
Yeah.
is that it? Is that the standard deviation of x bar?
For each one that. Meaning that SI down there.
Here? Well, no, we're gonna use sigma. So we're gonna use mu naught, that's what this is. That's mu naught. And we're gonna add z, and this is gonna be sigma. But that's the standard deviation of x, not the standard deviation of x bar. How do we calculate the standard deviation of x bar from the standard deviation of x? Well, let me point out something else. Why did Quality Associates suggest we use 30 observations?
Normal?
Right. To make sure that the distribution of x bar is normally distributed, even when we don't know anything about the distribution of x. Now, are we dealing with x or x bar here? X bar. Which one has a smaller standard deviation? X or x bar? If we're looking at, for instance, your heights, do the individual heights vary more than class averages, or do class averages vary more than individual heights?
Individual varies more.
Individuals varies more. What is the relationship? You know this, it's just
Sigma by,
is equal to what? Sigma,
sigma by 2n.
S divided by n squared?
Sigma, sigma of population divided by,
root of n.
there you go.
yeah, root n.
Oh, okay, sorry, I didn't quite catch that, yes. Divided by the square root of n, so in addition you have divided by the square root of 30, right? And that equals 12.0987 and 11.9013. So that our data looks like this. Like that. And this type of chart, an X bar chart, is what you would use, right, when you monitor your machine across time. As soon as that machine went, had a mean that went above or below your control limits, then you would recalibrate. If you get an X bar inside your control limits, is it possible that the machine is miscalibrated?
Yes.
Yes. I mean, clearly, if you sample, you can always get an average that's inside here, no matter what your calibration is. It can be completely out of whack, and still, you're going to get what looks, it's going to look fine based on your small sample of 30. In addition, if your machine is well calibrated, is it possible that you're going to get an observation outside of your control limits? Yes. The problem is, you don't really know, right? But that's the fun and games of quality control. You have to make a decision based on limited sample, especially if you're dealing with something like eggs. You sample 30 eggs, you really can't put them back. So you have to be careful that you limit your damage.
Destructive testing.
What's that?
Destructive testing.
Destructive testing, that's right. Okay, what would happen if we increase alpha here? So alpha goes from, say, 1% to 5%. What would happen to our control limits?
Small.
Very good. So we would move further in, and the ratio at which we make a type 1 error would increase, yes? We would then reject the true null more often. But what would happen to the ratio at which we make type 2 errors? It would reduce, right? Because even if you don't know exactly what the relationship is, and it most certainly is not linear, as long as you fixed n, alpha, and beta, if you increase alpha and hold n constant, you will decrease beta. And since we talked about how type 2 might be more serious here, that may be a good idea. Questions on hypothesis testing for means? Quality control? Hypothesis testing in general? Checkers Guide to the Universe? All right, then we're done for today. Thank you.